So today's this is the next class of the communication principles of communication chapter. We're gonna try to solve some of the ER questions. All the questions that we'll see for the PSTN network, mobile PSTN stands for public. What does PSTN stand for? I think public service telephone network. I think.
স্যার কালকে হচ্ছে যে আমরা একটু বাইরে যাব, অন্য কোনো পসিবল ডেট কি দেওয়া যাবে?
Saturday 2 p.m. to 7 p.m.
আচ্ছা স্যার, হ্যাঁ ঠিক আছে স্যার, থ্যাংক ইউ স্যার।
So PSTN stands for public switched telephone network. This is a name of the basic telephone communication network that we use, which used to be a part of the syllabus. So you don't need to do these questions. You can cross it off. I'm not going to discuss this anyway. We're not going to need that. Question number 2 says a signal that is transmitted over a long distance will be attenuated and it will pick up noise. State what is meant by attenuation and what is meant by noise. We have 3 marks in these definitions. Attenuation basically means the loss of signal power when transmitted over long distances. Because this is a state question, so I would not say why this occurs. If this was stated and explained, I would have to add that the loss of power happens because of the spreading of the energy as it comes out of the aerial. And also the second reason is that as it goes to the medium, because of the medium particles can sometimes absorb some of the energy, and that is also responsible for energy loss, which actually is one of the very key factors for why optical fibers do require, why optical fiber mechanism or optical fiber communication channel does require repeater station after a while. You need to understand that by definition, the mechanism principle by which optical fibers work is total internal reflection. So essentially that means that all the photons or all the energy that we're going to send through the input side are supposed to be completely conserved within the optical fiber pathway, because it is total internal reflection, no light is going out. But in theory, it's supposed to be 100% efficient. You should not have any loss at the end point of the receiving point, which means that an infinitely long optical fiber should be workable. But that's not practically the case. It could have been practically the case if there was no impurity in the optical fiber that we use, which means it was a perfect pure silicon dioxide crystal. But that's not the scenario, because to make sure the way optical fibers work is that the core is made up of a denser optical medium, which is a cladding. Cladding means uniform thickness coating of smaller reflective index material. So you have a denser core and you have less dense periphery, which basically makes the light beams to experience total internal reflection as they're getting outwards from the core, and then they reflects back towards the core and then reflects on the other side, and keeps on happening million times as it travels to the optical fiber. But the thing is that to make sure that we can achieve this variation of the reflective index, we have to introduce some impurities which controls the reflective index of this medium. And those impurities are essentially, and also along with those, also some unwanted impurities can also be present. These impurities essentially are responsible for a significant reduction of the light signal. This is why beyond a certain length, we have to place repeater station. Repeater stations are basically communication hubs which pick up an input signal and then converts it into, doesn't convert it, it basically amplifies the whole signal, keeping the original signal intact. As we've seen in the last class, that if you're sending an analog signal, the noise will also get amplified. But if we have a digital signal, the whole thing is regenerated and then amplified. That way the noise can be discarded every once in a while. How long after do you have to place all of these regenerative stations depends on multiple factors. For example, what is the input power that we are sending for the light signals? How pure is the material of the optical fiber itself? And also, what is the ambient noise of the receiving end on the for the regenerative station? You might also wonder that then if the impurities actually provide that kind of a problem, then why is it not a good idea to make really pure or 100% pure silicon dioxide crystals to give us a much better length of the whole thing? There comes a very good question that theoretically it is very much possible. I mean, making an optical fiber with 100% pure glass silicon dioxide is not essentially impossible. It's possible to manufacture, but the cost of that manufacturing process would be, what can I say? It would be mountainous, or like is superbly huge. You have to understand that in the process of purification, if you try to think about removing the impurities, the amount of cost that you have to go to make something, let's say 90% pure, you might have to spend double of that amount if you want to make it 95% pure, maybe triple of that amount if you want to make, let's say, 97% pure. Because the further impurities you have to go, the cost of the manufacturing increases exponentially, because removing the last bit of impurities become very, very difficult. So if you have to take care of everything, you really have to spend a lot of money, which essentially makes the optical fiber really, really costly to produce. So in theory, it is not impossible to manufacture a product like that, but it would be economically not viable to use it for large scale operations. So there is a sweet spot that how much of impurities can we achieve, and how many UPS stations is actually acceptable in terms of lag and latency of the communication process, and we basically operate on that border. I don't know the exact values for what is the exact purity value for those optical fiber communication channels, but if you are interested, you can look it up in Google's and other places very easily. It's not that of a big deal. So attenuation, so in this case, because it's only a state question, so for the definition of attenuation, you just have to say it is a loss of signal power or while transmitted over long distances. And the noise has basically, as far as I can remember, we'll see the mark scheme in a while. There are basic 2 points, 2 characteristic point of the definition of the noise. One is that the noise is an unwanted signal power, which we do not want, and it is picked up from the surrounding of the communication channel. The unwanted is the keyword because we do not want the noise to get into our communication channel, but this is something that we cannot help with. It is inevitable by its own virtue. So let's have a look at the definitions that the mark schemes give us. Here they have only meant the loss of signal power. They did not even bother to mention over long distances. So you just write that part and you get the mark. And then for definition, for the noise, yeah, I forgot to mention the random part. Sorry, the 2 parts which is very unique for the word noise. One is this unwanted power, and it is random. Random is the important bit. Because it is random, it is difficult to deal with. If it had a certain pattern, then we could use some sort of mathematical equation and use an alternate opposite signal generator to cut it off from our signal. But because this is random, it is difficult to get rid of in an analog signal, that is. So these are the 2 key points that you have to write. If you look for the examiner's report, it says that only a few candidates understood this part, whilst it was realized that a digital signal consists of no. It's 2A. Oh, sorry. This part was answered well by most candidates. So yeah, people knew what to do. In question number B, it says explain why regenerator amplifiers do not amplify the noise that has been picked up on digital signals. Because regenerator amplifiers basically recreates the whole signal using their own voltages while observing the input signal. So the masking language goes like this: for digital, here it is. For digital, only the high and the low, or 1 and 0, are necessary. Variation between highs and lows caused by the noise is not required. So this is basically the type of language that the examiners would like to have. Let me explain what this means. For digital signals, only the high and the low, or ones and the zeros, are necessary. Variation between the highs and the low caused by the noise is not required. What this paragraph essentially means, let me show you from the graph. Might be a bit better understandable. Somewhere over here we can see that whenever a digital signal is going to pass through a communication channel, because of attenuation, all the high voltages are going to lose some bit of their voltage, which is obvious. And also because of the random power generation, random noise pickup, we have some bit of you see these cranky marks or zigzag lines over here, which basically represents the pickup of random signal power from the communication channel. Whenever the regeneration will be done, it would basically observe these signals and recreate the whole signal in a flat pattern. So what is very important for the regenerator as input is that do we have a high voltage or do we have a low voltage? So it only needs to see the high voltage and a low voltage. The difference between the high voltage value and the low voltage value is not required. So these 2 voltage levels has to be distinguishable. As long as these 2 voltage levels are distinguishable, the regenerator can work pretty well. And that's basically where the limit comes in, that as the signal travels through the communication channel, the farther it will travel, the lower this high voltage level will slowly go down. And so there will definitely come a certain distance when this high voltage level and the low voltage level would not be identifiable differently. So we do not want to go to that distance. We have to place a regenerator station before that, so that the high voltage and low voltage are still distinguishable, and from that information we can very well recreate the whole signal. So the individual distances between the voltages are not essential. Only the difference between the high voltage pulse and the low voltage pulses are essential. So once again, have a look at the examiner's mark scheme language. For digital, only the high and the low, or you can write ones and the zeros are necessary. Variation between the highs and the lows caused by the noise is not required. So that does not essentially bother us. The examiners reports say only a few candidates understood this part. Whilst it was realized that a digital signal consists of series of highs and lows, a widespread misconception was that only these highs and lows are amplified. Widespread misconception was that only these highs and lows are amplified. These highs and lows are not amplified. We take the input from the highs and lows and recreate the whole signal, regenerate the whole signal using the supply voltage of the op amp. You don't have to mention the op amp. I'm just telling this to you so that you can make sense how it works. Because we are acquainted with the idea of how the operation of the op amps. I'm going through a continuous description for discussion for these questions, which I feel necessary for discussion. If you have any question, please raise your hand, and then you can have a floor and you can ask your question. That works. The C number question says, I think we did this question last class, so I'm not going to get through this once again. You can look it up in the yesterday's video. Question number 3 is altogether discarded. I believe this whole block diagram that you can see is for the PSTN network, so we don't need these stuffs. We don't need these stuffs either. This question, however, sometimes also show up in your syllabus yet, that what is the purpose of the parallel to CL converter, and also what is the purpose of the CL to parallel converter. So this question might be a bit of interest for you. Although it now belongs to this part, but this question is still a part of your syllabus as far as I know. What I'm trying to mean is that, have a look, this block diagram is still over here. Between this parallel to serial converter, right over here, what happens right over here is basically this whole thing. So you do not have to bother between these two parts. So this part where I'm moving my mouse is what you don't have to learn. You have to learn up to the parallel to serial converter, then it gets into the communication channel, and that communication channel is basically a PSTN network, which you don't have to learn. And then it comes out of the parallel communication channel, and then it goes to the serial to parallel converter. So you just have to know their uses. So I'm going to look for the answer for this one. What is the purpose of the parallel to serial converter? As we've discussed in our last class, the parallel to serial converter takes up all the individual bytes, or you can say nibble, or you can say use that, or the individual digital signal produced from the sampling, and converts them into a single array of ones and zeros, so that it can be transferred over the communication channel effectively. So it's about taking all of those things and lining them up in a single file. If you have a look at the mark scheme, it says that here it says that all bits for one number arrive at one time. That's for the parallel idea. Bits are sent out one after another. This is a bit confusing because this is about the PSTN. Forget about this. We don't have to do this over here. You can cross out this whole question. Number 3. We're gonna see about this question's relevance whenever it comes to the appropriate questions. Forget about number 3. But we will have to see about this usage eventually. Question number 4 says a radio station emits an amplitude modulated wave for the transmission of music. State what is meant by an amplitude modulated wave. Definition. Let's have a look. Amplitude of the carrier wave varies in synchrony with the displacement of the information signal. Now, this is a very important information. You have to be very careful to choose your words very carefully. I'm using too many carefuls because I want you to be careful. Amplitudes of the carrier wave varies in synchrony with the displacement of the information signal. You cannot mess up this word. If you write over here that amplitude of the carrier wave varies in synchrony with the amplitude of the information signal, you're going to lose that mark. You have to understand this very perfectly, that the displacement of the information signal causes the amplitude variation of the carrier signal. Let's have a look at this figure so that you can get a bit more what can I say, refresh of your memories, you can see over here that this is the amplitude modulation. This plus this gives you this. So this was an unmodulated carrier where we have all the amplitudes of the individual waves in the same way. Here we have a variation of the amplitude of the individual waves because of the displacement of the information signal every once in a while. It is the amplitude of the information signal is still very much over here, but the amplitude of the information signal is not affecting this one for every single cycle of the carrier signal. When you are doing the modulation, each individual cycle of the AM wave basically are getting a new amplitude based upon the instantaneous displacement of the information signal. So be very careful in the choice of your words. Once again, it is amplitude of the carrier wave varies in synchrony, or if you don't want to write in synchrony, it's in bracket, or you can write that alongside, or you can write along with. It works. Whatever, any replaceable words with the displacement of the information signal. That's basically what we mean by amplitude modulation. Then it says the variation of the frequency f of the amplitude of, number 2, give 2 reasons why the transmitter wave is modulated rather than transmitting the information signal directly as a radio wave. So why do we have to do the modulation? There can be a lot of different reasons for how we can give modulation. There are a lot of advantages of modulation. Here we have some of the examples over here. They've given examples because there can be other options as well. More than one radio station can operate in the same region or less interference. That's what we've learned in earlier. It enables shorter aerial because if you have to transmit a larger wave, you need a bigger aerial. If you want to work with a smaller wavelength of wave, then you can work with a shorter antenna. This is essentially why all of our cell phones can work because they work in microwave signal. We can have the antennas hidden or concealed within the cell phone body. That's the advantage of using microwave. One of the advantages of using microwave. And then it says,
Sir.
yes.
Sir, aerial and antenna same জিনিস না? Yeah.
Aerial and antenna exactly same finish. Yes, they are just synonyms to each other. Aerial and antenna.
Sir,
Yes.
স্যার আমি এটার ফার্স্ট পয়েন্টটা ঠিক বুঝি না যে একই জায়গার মধ্যে অনেকগুলো থাকলে মানে অ্যাডভান্টেজটা কি হবে?
We can have multiple radio stations operating within the same geographic location because they'll be using different carrier frequencies, so the users can tune into different radio stations and hear different programs as per their choice. You don't have to have it will not essentially occupy a single radio channel.
আচ্ছা স্যার।
Okay. And then we have increased range or less power requires or less attenuation. This is actually the primary reason that I told you that one of the primary advantage of having the modulation is that we can add up the information signal with the high frequency signal, which is a carrier wave that enables it to be transferred over really long distances, because that high frequency wave has a much bigger amount of energy, I proportional to frequency squared. As a result, we have longer range, and then we can also have less distortion. The idea of less distortion is important because this is you have to understand that between AM and FM, as we have seen in this paragraph, as we have seen in which paragraph, I think in this paragraph, whatever in this heading, what you've seen that between AM and FM, AM picks up more distortion and FM picks up less distortion. FM can give us a much better quality of sound in terms of bandwidth and also in terms of noise pickup. It picks up less noise, but AM does both of them poorly. But here we are trying to say the advantages of radio wave without having the modulation. So what we are trying to compare over here is that if we did not have modulation compared with if we do modulation. So if we did not have modulation, if we only send out the information signal, there would be more distortion because the signal would become it would become more, what can I say, polluted, more changed by the noise pickup compared to the modulated wave, because the modulated wave would essentially cause the distortion to be less. Anyway, there is an example. This is given as an example over here, so which brings us to the idea that there can be more points. Let's look at the examiner's report. The most commonly stated correct reasons for transmitting modulated wave were that it would have less attenuation, a greater range, and less interference from other radio waves. And the important advantage is that it will enable the use of a smaller aerial. Some candidates did not make it clear whether their comments referred to the modulated radio wave or the information signal radio wave. Okay, so up to this point is the actual answer, and this is actually the sum of the I shouldn't say bitching. what is the correct word? The warning that the examiners are making for the other kids to be careful about. So some guys did not make it clear whether their comments refer to the modulated radio wave or the information signal radio above, which means you have to be specified that are you saying the benefit of a modulated wave, or are you saying the advantage of a radio wave? So you have to be specific about your wording. So that's that, and then comes number B. The variation in the frequency f of the amplitude of the transmitted wave is shown in figure 111.1 for the transmission wave, determine the wavelength of the carrier wave. So here we have the frequency of the carrier wave, which is 909 kilohertz. This is a radio wave. So essentially, you know, V equals to f lambda, where in this case, V is the speed of light. So we can very easily calculate the lambda over here. The bandwidth would be, for the transmission, the bandwidth would be the total range covered by the whole signal, which is 900 to 918, that is 18 kilohertz. You just can write 18 kilohertz. The maximum frequency in hertz of the transmitted audio signal. Maximum frequency in hertz of the transmitted audio signal. Now, this is an important bit. Here's the deal. The bandwidth basically shows you 2FA. So the FA, the audio signal frequency, would be only half of it. So in this case, the audio signal frequency would be 18 kilohertz. So bandwidth would be 36 kilohertz, and maximum frequency of the audio frequency signal should be 18 kilohertz. I think I'm correct. 18 kilohertz, and then, sorry, why did I mess up? Oh, sorry, 909 to 918. So this is FA. I was saying it right, but calculating it wrong. So this would be 9 kilohertz, or because they have written only hertz over here, so you cannot write 9. You have to either write 9,000 or 9 Newton to the power 3. Either of these things will work. Yeah, makes sense.
Sir, I didn't get it.
Bandwidth basically, let me show you. Here's a bandwidth representation. Have a look. So this is the sidebands, and the total bandwidth gives you 2FA. So the full bandwidth gives is the double the maximum frequency of the information signal. So if you want to calculate the exclusive maximum frequency of the information signal, that is basically the value of FA. So that is basically half of the bandwidth, or you can say from the carrier to any of the sides. So that's what I meant. So this is FC plus FA, this is FC minus FA. So only the FA is the maximum frequency of the information signal.
Not FC plus FA, sir.
FC plus FA is the value of one of the sidebands, which is on the higher side, and FC minus FA is the value of the other sideband, which is on the lower side. These two are sidebands. They are not the information signal frequency. These frequencies come along by the choice of the carrier wave. For example, if the carrier wave is, let's say, 1000 hertz, and your or information signal is, let's say, 100 hertz, then you can have 1100 over here, and you can have 9900 over here. But you can choose the carrier signal to be 900 hertz over here. But you can choose the carrier frequency to be something else. In that case, your sidebands will also shift alongside. But the gap over here between the carrier and the sideband, that will pretty much remain the same, because this is a representation of the maximum frequency of the information signal.
So maximum frequency is FA, sir.
Yes.
Okay, sir.
For this figure, this is represent. For this figure, we are only having a one line, because this figure was actually created for a very unrealistic but simplified sinusoidal wave, where we had only one signal frequency of the information signal. That's why we have only two lines over here. That's the sideband basically. But whenever we have a more realistic variation of sound, we get this kind of variation. That's what is shown in your figure. This is also a bit more unrealistic because it shows a very smooth curve, but you can see over here that how this graph can actually look quite distorted, because you can have a lot of mingles of, you can have a lot of different frequencies merged together within a single sound source, music or band show or voice channels or whatever program that you're trying to, or advertisement, you name it. Yep. বুঝে গেছে?
Ji, sir.
Let's go for the next one. Number 5. I'm going in sequence over here, but I'll not be doing this for the entire worksheet. I'm trying to go through some of the unique problems. So any single time a recurring problem comes by, I'll skip it immediately to the next one. So I'll try to cover as many of the unique problems there is in this worksheet. So bear with me. And if you need me to slow down, need me to repeat, have any questions, please feel free to share and raise your hands. Works that way. An optic fiber is used for the transmission of digital telephone signals. The power input to the optic fiber is 9.8 milliwatt. The effective noise level in the receiver circuit is 0.36 microwatt, as illustrated in figure 12.1. Okay, so we have the inputs 85 kilometer optic fiber receiver circuit. Okay, the signal to noise ratio of the receiver must not fall below 28 decibel. Here's the deal: the signal to noise ratio at the receiver must not fall below 28 decibel, which means the received signal should be at least 28 decibel stronger compared to the noise of the receiving environment. For this transmission without any repeater amplifiers, the maximum range length of the optical fiber is 85 kilometer. Calculate the minimum input signal power to the receiver. So what would be the minimum signal power received over here? Now, here is the deal. Before I show you this whole working, I'd like to take this whole question, but I cannot pick up this whole process in pieces. This hurts. I don't want to deal with piece questions. So let's try to find out the original question so that I don't have to pick up every single piece. This is question number what? 5. So question number 5. I have the whole thing here. Boom. Can I copy from here? Paste it in here. Will this work? No, it doesn't work that way. So I have to open this and if I give edit. How? Okay, now it should work fine. So let's close the other one. Make it large. Small. Okay. So before I get into this working, I'd like to show you the mathematical formula. I'm going to write the formula over here because I'm going to be needing this formula for quite some time. So what? Oh, my USB got moved. Yes. So the basic formula that we work for the signal communication is that the first one that I gave you is attenuation. Attenuation is given by 10 log P out. No, sorry. P in divided by P out decibel. That's the attenuation formula. That's number one. And the second one that we need to know is the signal to noise ratio. That is given by 10 log P out, because output power has to be always stronger than the noise of the environment, noise decibel. So these are the two key formulas that we'll be using throughout our mathematical proceedings. So here's the thing, have a look. You have the P out in both of these equations. So it is logically possible that we can calculate the P out from either of the formulae, but we have to see over here that what do we have at hand for this question. Have a look once again. Try to understand the information. On the input side, we have 9.8 milliwatt. This is the input power to the signal. It is traveling to the optical fiber channel, which is a communication channel of 85 kilometers. Beautiful. Then we have a receiver circuit, which is receiving the receiver circuit noise. The noise of the receiver circuit is 0.36 microwatt. This is not the output power. This is the noise around this channel. So the question essentially gives us the input power, and it also gives us the noise power. So these are the two things which are provided with you in the question. The question then says the signal to noise ratio at the receiver must not fall below 28 decibel. So this value that they are given to us, this is the signal to noise ratio, which means they haven't given us the attenuation of the channel. We don't have the information, but we have this value. Then it says calculate the minimum input signal power to the receiver. Minimum input signal power to the receiver. How many marks do we have? Only 2 marks? Okay. This is also another no. This is okay. This is also another what can I say, confusing set of words. Have a look at, have a read. What does this set of word essentially mean? Minimum, I should cover the minimum input signal power to the receiver. Does this mean the input power over here, or does this mean the input power over here? Which one does it mean, essentially? What did I do? What am I having? This one, this sentence, does it mean P input or does it mean P output? What does it mean? By reading this information, what do you understand from here? Kids?
Output.
Yes? Anyone else?
Output, sir.
It essentially means output. For it, the reason I'm trying to take my time and give you some time to think about it because of the wording, because they have used the term input over here, but this is not anyhow referring to this input circuit. No, it doesn't. Input signal power to the receiver basically means what is the output signal power of the communication channel. So this basically means the output. So using this ratio over here, we can go ahead and calculate the output ratio. So this would be 28 equals to 10 log P out divided by P noise. So if I now do this, this is 2.8 equals to log P out that I want to calculate, and on the denominator side this is 0.36 microwatt. The final answer has to be in watts, so I can write the microwatt in micro 0.36 into 10 to the power minus 6. Solve this out to get the value of P out. I want you to solve it. I'm not going to show you how to do the log conversion, but please try to solve this. And if you can solve this, ask me, I'll show you. But if you can, please try to find out the value of P out and share the number on the chat window for everyone, not for exclusively me. Okay, so I was just proposing 2.27 10 to the minus 4. I'm going to write this down. I would like other people to confirm his value. This is all right? Ramesh has given us 2.24. Ryan is getting 2.27. I'd like you to have a read for my poor handwriting. This is 0.36. Maybe you wrote 0.38 or something. I'm not sure. Can I have a look again in your calculation? It is 0.3.
Yes, sir, 80 Asians, 2.27 10 to the minus 4.
Yeah. So that's the value of the output signal that we get. We'll move on. Then the question says that use your answer in A to calculate the attenuation in the fiber. So now we can very well calculate the attenuation since we've got our P out. So we can calculate and go ahead and attenuation. So you can simply write attenuation in short form. Attenuation equals to 10 log P in by P out. You see, I have preferably changed the expression of these powers other than the way these formula are represented in your booklet. In your booklet, these formula were given by P1 and P2 and in such other forms. I personally don't like this because this can prove to be pretty confusing that which one is goes on the top, which one goes at the bottom. I like them in output, noise, and input in these three versions because that makes the calculation and locations much too simpler to remember and work by. So you have this, and then if we just simply, now from this equation find out the P in, help yourself, do some mathematical magic. Sorry, you have the P in, sorry, P in ta koto dewa chilo, the P in was 9.8 milliwatt. So yes, we can pretty much do this. 10 log 9.8 into 10 to the power minus 3 divided by, here we have 2.27 into 10 to the power minus 4. How much do you get for the attenuation value? How many decibels? 16.35. So I'm going to go for 16.4. Someone else confirm? Okay, 16.4 seems to be correct. Beautiful. And then it says determine the attenuation of the per unit length of the cable. This is very simple. You just divide that value by 85 kilometer and get the number over here in standard form. I'm not doing this. You can do this on your own. So that's basically how we do this maths. So you have to understand what are the information that you have at hand. Remember the two formula. And then you can simply go ahead and solve this formula. One of the few things that I could recommend, that if any of the cases that you forget the shape of the formula or it becomes a bit difficult, you can always, to be honest, write up this formula in the blank pages of your question paper. It typically has at least quite. I mean, there are a few blank pages in places or spaces after the question. You can write those up in pencils and later you can cross them out. It doesn't matter what you write in the blank pages, unless you make an explicit request to which is to the examiner that please give me good marks or let's say weird stuffs, and draw up you know what Doraemon or what is this? What is this yellow sponge? SpongeBob. Unless you do weird stuff, you can always write these stuffs over in your blank pages. Whether you cross it out or not, this would not actually bother the examiner. Examiner will not even be bothered to know. As long as you write relevant stuffs or you can do your rough work in the blank spaces, it's no big deal. You don't have to cross them out, but if you cross them out at the end of your exam or in your working procedure, you can just do that, no big deal. So that's that question. Let's go for the next one.
স্যার
Yes.
আমাদের যে 10 লেখা ছিল লগের আগে ওটা কি ফর্মুলার পার্ট?
হ্যাঁ, ওটা ওই যে ডেসিবেলে আমরা করতেছি সবগুলো ক্যালকুলেশন, সেজন্য আমরা 10 দিতেছি. If we use bell, then this 10 would be gone. Everything that is done in decibels, you see decibels.
ও আচ্ছা স্যার।
That's why.
Can I see the signal transmission formula?
Yeah. I understand that some of you are not present in our last class, so I'll show you this part of this formula discussion from the last class. I'd like you to have a look. I'm gonna pause recording right now. Get rid of this video. We don't need this, so I have the browser open and go for the next problem that we have. So I think we saw this problem in the last class. So yeah, this is the question. What is the purpose of the parallel circuit converter? I believe we solved this in the last class, so I'm not going to talk about this, but I'd like to have you, for today's class, I'd like to have you look at the mark scheme 6A. So you have over here, it takes all the simultaneous digits for one number and sends them one after another along the transmission line. So that's basically it. Making all the parallel numbers, converting into a single sequence of number. The examination report says most. There were some convincing answers, but many the statements were limited to something being sent one after another. The bits in a word were rarely mentioned, so the word bits should be mentioned. It takes all the simultaneous digits of one number and sends them one after another. So that's the idea. And then we Ashana, we should do this question in detail. Can I select this individually? Select. Can I select this? Home. Edit. No, I don't want to edit this. So can I select this only? Select. Oh, okay. Might as well select from the original question. This is question number 6. Okay. So let's I'm going to get rid of this quotient, but I'm going to keep the formula because we're going to need the formula. So let's skip the formula right over here. Put this new quotient right in here. And the second part is this. Okay, let's place them side by side. This would be easier for us to solve it anyway. So let's go have a look at this question. Part of the signal for the microphone is shown in figure 11.2. So this is a certain microphone signal that is going by. You can see that we have the time base given, the time measurements given, and the output of the microphones are given as well. The question says the ADC or analog to digital converter samples the analog signal at a frequency of 5 kilohertz. Each sample from the ADC is a 4-bit digital number where the smallest bit represents 1 millivolt. So 1 millivolt is our step size for the y-axis. The first sample is taken at time 0. Use figure 2 to open true to determine the 4-bit digital number produced by the ADC at time 0.4 millisecond. So if you have a look at this graph, at 0.4 millisecond, this value is exactly 5. You can, sorry, 7, between 6 and 8 is perfectly 7. So all that you have to do is to convert that by the decimal number 7 into digital value and do that with your calculator. Help yourself. So I'm going to try to do mine and you try to do yours. I'm trying to convert 7, so decimal 7, binary 0111. That's what I get. I have to give this extra 0 in the front because the question says that this is a 4-bit digital number, so all of these bits, this has to be digital number. And then at 0.8 millisecond, we're going to need all of this information to draw this graph. That's why I'm going in thoroughly through this question, because we'll see how to draw this graph. Knowing how to draw this graph is pretty important, like really important. We have a lot of questions about this part. At 0.8 millisecond, we have the value right up over here. So here is the value. If we go all the way over here, this is actually this point. This is between 7 and 6, and as you've seen in the earlier class, that the preferred number is always the lower increment, which means we have to choose 6 for this value. So if you convert 6, you're gonna get 110. So here this answer should be 0110. Am I correct? I think I'm correct. Decimal 6, binary 110. Yeah, take us. So these are two numbers that we convert, and then we immediately get these 2 marks, easy marks. And then the question comes in: the digital signal is transmitted and then converted into the analog form by the DSC, digital to analog converter, using data from figure 12.2. Draw on the axis of figure 12.3 the output level of the transmitted analog signal for time 0 to time 1.2 millisecond. Now, to be able to draw this easily, I'm gonna do one thing so that I can make better sense with you. Is this the same? These two are the exact same graph. So I'm gonna first show you how to do this. Then I'm gonna take a mod version of this one, and I'll show you what we're gonna do. So I'm gonna say keep this blank graph over here, and the way these graphs are always done is, first of all, you have to convert the 5 kilohertz into its time frame. So find out what is your sampling time. Sampling frequency is 5 kilohertz. So if you do 1 by 5,000, getting back to computation mode, 1 divided by 5,000, that gives you 2 to the power minus 4, which gives you 0.2 millisecond. So 0.2 millisecond is our step size. So this would essentially mean, can I zoom in a little bit more and be able to see both of these graphs at the same time? Bit difficult. Bringing them close can help, I think. Okay, I'm gonna bring them in close so that I can see them together simultaneously. This actually helps a bit better. So the way this graph is going to be drawn, I'm drawing with basic pencil because I have to continuously move my hand, but whenever you're going to be drawing these graphs, always, and I mean always, prefer to use a ruler, because no line in this graph would be zigzag or curved or freehand. All these lines over here should be straight lines, horizontal or vertical. So do preferably use a ruler. So the first signal is read as 0. So we're gonna have a line from 0 to 0.2. At 0.2 second, the impulse is at 8. So it directly goes up to 8. A vertical line goes up to 8. And that 8 is maintained up to the next impulse moment, sampling moment, which is right over here. This is 0.4. At 0.4, we have 7. So it goes down to 7, which is right up here, about halfway. And that 7 will be maintained for the next sampling duration, which is 0.6. Here is 0.6. 0.6 at 0.6 we have a value of 15. So it rises up all the way up to 15 from here. So 15 would be somewhere over here. So you make it rise all the way up to 15. All of these lines are supposed to be vertical. So you can use dot circles to label the points first and then do your line drawing. That also perfectly works. Examiners should know that you know your stuff. At 0.8, this is 6 once again. So at 0.8, it is going to be 6. Oh, sorry, my bad. Once it becomes 15, it will remain as 15 for the next duration of the sampling. Then it drops down to 6 vertically. And then it will remain as 6 for the next duration. So up to 1.0. And then we have, can we choose a bit more thickness, maybe? Zoomed out. At 1.0, we have this right up here. So we have to find out what this value represents. In the graph, 1.0 is, this is between 4 and 6. And you can see that this would be 5. So this point sample of point is actually between 5 and 6. So we choose the lower one, lower increment always. So this will be 5. So from 6, it goes down to 5 and maintains at 5 over here. Many of the kids actually finish their graph right up over here, but I highly recommend that you at least draw the vertical line for the last sampling, because at 1.2, this value becomes over here at 8. So preferably finish your graph with the vertical line. This, you don't have to show the horizontal part because there's no more graph left, but at least show the vertical increment, and that's basically your conversion. So this is basically the graph that we have to draw. Actually, I saved this graph over here, but we're not going to need this. But what I really want you to see, if I just select this graph with a transparent selection and replace that one after another, you will be able to see what these two graphs actually are, one with respect to the other one. So let me just do that, and you can have a look. Okay, keyboard. Almost perfect, a bit more. So that's what I mean. I just replace the graph onto this one. So you can see that whatever you got over here, maintain for 0.2 seconds. Whatever you got over here, maintain for 0.2 seconds. Whatever you got over here, maintain for 0.2 seconds. Whatever you got over here, maintain for 0.2 seconds. That's basically how the whole recovering does. বুঝা গেছে গ্রাফের কনস্ট্রাকশনটা?
Sir, sampling rate was 0.2 millisecond.
Yes.
Okay, sir.
এই গ্রাফের কনস্ট্রাকশনটা বুঝা গেছে কিনা সবার? If any question, anyone, please. It's important that you understand how this was done.
Yes, sir.
Okay. Then it says, state and explain the effect of the transmitted analog waveform of increasing for the ADC and the DAC, both the sampling frequency and the number of bits in each sample. So this is basically the, have you read the question? State and explain the effect on the transmitted analog waveform of increasing for the ADC and the DAC, both the sampling frequency and the number of bits in each sample. So we have to explain what happens and why that happens if we increase the sampling frequency, and also if we increase the bit number. So the first thing is that if we increase the sampling frequency, we will measure the original analog information more often. So the produced data would be bigger in volume, but the output signal would be less grainy or represent more like as the original analog form. That's the basic benefit. And similarly for the bit system, if we use a bigger bit system, in that case we'll have more levels on the y-axis. So each small variation of data would be more visible or would be recorded on our ADC, analog to digital conversion, and when converted back into digital, it would be possible to get the original signal almost in its original shape. So the benefit of having a bigger bit number or a bigger sampling frequency is essentially that it makes the output less grainy, or to represent more closely to the original analog signal, and it can essentially capture every small bit of variation in the original analog signal. What does that essentially mean? That what you can see over here, that here we had an uniform increase of this of the data. Let me use a different color, maybe green. Here we had a uniform increase of the original analog signal, and then you can see over here there is a bit of a tip up, and then it went down. But in the digital signal, all that we had produced is that there's a flat line over here, then there is a sudden increase, and there is a flat line over here. This flat line does not capture this variation at all. So we are losing this information altogether, like altogether. But if we had a higher sampling frequency, we would observe the signal more often. And if we had more steps over here, we'll be able to capture this point more precisely. Maybe in that case, we might as well get, I'm using blue, we might as well get a graph that looks like this. I mean, that might be more resembling to the original shape. So that can happen like that. So if we look at the mark scheme for this question, let's have a look at what the mark scheme holds us for this answer. This is question number 6D. Increases the number of bits reduced. Increasing the number of bits reduces step height. Reduces step height means you have more steps for the same amount of vertical spacing. Increasing the sampling frequency reduces the step depth or width. So they have used these two words, height and width. Step height essentially means how many levels do you have over here. If you have more bit number, you have more step heights. So you have more steps, which means individual steps would become smaller. That's why they say the reduced step size. And if you have, yes.
আমি এই ব্যাপারটা বুঝছি না, মানে স্টেপ সাইজের ব্যাপারটা বুঝতে পারছি না, স্যাম্পলিংটা বুঝেছি।
আচ্ছা, স্টেপ সাইজের ব্যাপারটা হচ্ছে যে if we, for example, this was done for a 4-bit signal. For a 4-bit signal, the maximum number of levels we can represent is from 0 through 15. So you have altogether 16 different variation of 0 through 15. If you had, let's say, an 8-bit signal, then you could have shown it from 0 through 31. So you could represent a total of 32 different levels, which means in that case, for the same amount of vertical gain over here, the number of levels that you could choose would be 32 different levels. Here, in this process, each 1 millivolt was equals to 1 increment of the binary system. But if we had a 8-bit system, then half millivolt could work as our 1. So each half millivolt would represent 1 binary value. So you would have all the way up to 32 levels, or 30 up. You could rise all the way up to 31. 31 would mean 1 1 1 1 1 1 1 1. So you would have double the number of levels for the same amount of vertical spacing, which means individual step size would become smaller.
স্যার মানে গ্রাফটা আরো বড় হতো।
If we magnify it, the graph would have been bigger. Or in other words, we can say that here, I mean, if I try to give you the exact meaning of the masking word, either we could maintain the same scale and make the graph go all the way up to 31. That's one way to do it. Or we could assume that the graph remains the same size, but the considered height of the millivolt increment, that can become smaller. In this case, for this graph, for this original graph, 1 millivolt represent 1 increment of the binary value. But if we had 8-bit system, that would mean that within the same space, we'd have double number of recognizable steps. Here we have 16 recognizable steps, but if we had an 8-bit system, we would have 32 recognizable steps, which means each of the step size would have become smaller.
বুঝেছি স্যার।
Beautiful. Anyone else? Does this make sense? Have a look at the mark scheme. Reproduction of the signal is more exact. You can write this. I would actually write that the signal would be less grainy. I would not write this word, but anyway, they prefer this version, so you might as well remember this. If you look at the examination report, there are some excellent answers based on the step height and step width. The majority refer to the better quality of waveform without giving detail as to why this would occur. Acha. Most of the students mentioned that the original, the recovered signal would be better quality or represent more closely to the original analog signal, but many of the students did not give the reason. But you know what is the reason. So bit number reduces the step height, and increased bit number reduces the step height, and increased sampling frequency reduces the step height, which makes the signal far more better. But both of these things would make the file size far bigger. So that's another thing that we have to consider whenever we're trying to do the sampling. Number 7, in modern communication systems, the majority of data is transmitted in digital form rather than analog form. So there's 3 advantages of the transmission of data in digital form. Before we look at the mark scheme, can you think of 3 advantages?
Noise is not amplified.
Noise is not amplified, beautiful. One thing. Another?
Signal consists of ones and zeros.
So how is the advantages of analog? Another advantage of having digital is that we can do multiplexing. It means that using a single communication channel, we can send multiple. We can send multiple arrays of data using different things, especially for optical fiber channels, by either doing the 90-degree shift of the transverse waves, or we can do this by using different frequency of light so that they would not interfere with each other. So that's another. I can think of 2 advantages. The noise is not amplified, and another one is multiplexing. I cannot think of the third one. I'll have a look at the mark scheme. Number 7.
Are digital circuits more accurate or?
Digital circuit. I mean, I'll entertain your question. Digital circuits. I mean, digital circuits are accurate over long distances compared to analog circuits. Here's the deal that I need all of you to understand, that whenever we produce any physical sound, we're using the term of sound too many times because that's easier to understand. A basic procedure, the basic process of producing a sound information is mechanical, and that is a continuous variation of air pressure, which means if you measure it by piezoelectric transducer, you're going to get a continuous variation of voltage, like the way we have seen in the first graph. That is how analog signals are produced. That's what I mean by analog signal. If you want to transfer this analog signal over short distances, using it in analog form makes more sense, because you don't have to buy equipments, you don't have to convert them from analog to digital and reconvert it back from digital to analog, where you have to always consider some loss of information. So for a short distance, analog is beautiful. Analog works fine. But if you are trying to send information over long distances, which basically is the primary requirement for modern age because of long distance communications all over the world, in that case, digital is more reliable. Analog is not, if you say that analog is not reliable, period, that's not essentially true. Analog is reliable over short distances. It works. But over long distances, it's no longer reliable. That's the difference. So you have to mention that distance factor. That's important.
Okay, sir. Thank you.
Sure, no problem. And also, digital data can be encrypted for security. Encryption is also another very large advantage for digital data. The digital data can be encrypted. One of the ways that encryption works, this is actually pretty interesting. I can tell you one single way of encryption. There are a lot of different encryption ways, but one of the primary ways by which an encryption works. Let's say you are sending a single array of ones and zeros, which is supposed to be a 8-bit signal. Now you want to encrypt it. How do you encrypt it? One way to encrypt it is to introduce random ones or zeros in certain locations. Let's say you're gonna in certain random locations which you're gonna have pre-recorded. So let's say you're gonna put in random ones or zeros in every let's say 2n plus 11th position, or some sort of mathematical equation there is there which basically guides the encryption system. So you're gonna just add random noise to the data in a way that it would be unrecoverable or undecipherable. It would not mean anything. So when it is actually decrypted, which means the encryption is taken out when it's decrypted. That decryption software basically plucks out all of those individual noise bits first, and then does the sampling, which gives you the beautiful data that you want. So that's one way to do the encryption, that you just add controlled noise in the scenario in a way that it is no longer viable, understandable data. So that is possible to achieve in digital signals, but not so much possible for analog signals, because analog signals are just waves. You cannot basically change them to a very lot amount. That way they lose their information, so that's difficult to work with.
Sir,
Yes.
your audio sounds a bit grainy, a bit bass boosted, sir.
How come?
I don't know, sir. It started off okay, but
It suddenly got larger?
like, yeah, halfway through the lecture.
Okay, how do I get my microphone control? I clicked my microphone, but I don't see my microphone control. Speech. Microphone.
Sir, you can reconnect, I guess.
No, it's a basic 3.5 millimeter jack. Reconnecting would not, it's not supposed to make any. Hello.
I think it sounds better now, sir.
Yeah, it's way better now.
স্যার এখন ভালো আছে।
Okay. Yeah, I just disconnected and reconnected. Something magical happened in the process. Okay. If it works, it works. Thank you. Automatically adjust microphone volume. Does that work better? Yes. Do you see the setting menu of the Zoom right here? Like there is a Zoom setting menu over here that I'm moving right now. Do you see
Yes,
that?
sir, I can see that.
Okay. Typically, Zoom stuff doesn't show up on the Zoom clients, so that's a problem. Okay. So if it works better, it's better. Thank you. Then we have this question. Our recording is made from some music. For this recording, the music is sampled at a rate of 44.1 kilohertz, and each sample consists of a 16-bit word. Such the effect of the quality of the recording of sampling at a higher frequency than the lower frequency using a low word length. So you just mentioned those two words. Sampling at a high frequency gives you what? Smaller step width of the ADC to DAC conversion, and long word length or bit size makes the shorter height of the, it decreases the height of the y-axis. How do I refer to the y-axis? High frequencies can be reproduced. Smaller changes in loudness amplitude can be related. What? Okay, so this is the same question but for a different wording. Okay, so let's have a look at these two questions. This question says, state and explain the effect on the transmitted analog waveform of increasing for the ADC and the DAC, both the sampling frequency and number of bits on each sample. So this question was about for the ADC and DC conversion, specified for that. So where we talked about the step width and the step height. This question was about the effect on the quality of the recording. So this is not about the conversion, but this is about the end result. Wow. Okay, you have to remember them differently. Such the effect on the quality of the recording of the sampling at a higher frequency than a lower frequency. So sampling at a higher frequency essentially allows you to record much higher frequencies, because the way we showed the earlier class that Nyquist proved that to be able to recover the analog signal from its digital conversion, the sampling must be done at a frequency at least double of the maximum frequency component of the audio signal. So using a long word length rather than a shorter word length, that's basically the bit number. So if you have a much bigger bit, so each individual variations or minor variations in the audio signal can be captured. Yeah, beats me. Small changes in loudness or amplitude can be detected. What does the examiners have to say? Was 7B1. In part 1, candidates were expected to state that that higher frequencies could be reproduced. In part 2, smaller changes in amplitude would be detected. Many candidates stated that the quality would be either better or worse. Frequently, a longer word length was associated with poor quality. So this is wrong. Smaller changes in amplitude would be higher frequency. So these people have been pretty specific about what they are expecting as the answers. So they have mentioned that what they are looking for in part 1, they are looking for something specific, and in part they are looking for something others that is specific. And for those parts that they didn't get the specific answers, they didn't grade the kids. Okay. Let's try to solve this question. The recording lasts for a total of 5 minutes 40 seconds. Calculate the number of bits generated during the recording. Try to solve this one using this information. It's sampled at the rate of 44.1 kilohertz. Each sample consists of a 16-bit word. So how many bits would you produce for a recording of 5 minutes and 40 seconds?
So what does the word mean in this case?
In this case, the word means the length of the sample. So if I show you over here, this one. So this was a 4-bit decoding system, DAC-ADC system. Sorry, ADC and DAC system. So this was the original analog signal. Here we sampled at 8 kilohertz, and it was a 4-bit system. 4-bit system means each of the decimal values were converted into a 4-bit number. So a 16-bit number would mean that this would have, each of these individual conversion would have 16 numbers in it, or it would have 2 to the power 16, 256 levels on the y-axis. Or you could detect individually from 0 to 255 number of individual different step heights on your y-axis. It basically means how big each individual sampling is. বুঝছো?
Not really, sir.
আচ্ছা, আগে লেকচারগুলো একটু দেখো, তারপর যদি ক্লিয়ার না হয় আমি পরে আবার বুঝিয়ে দেব, ডোন্ট ওয়ারি।
Okay, sir.
Okay, I would like to help for a bit for this question. This question, what I want you to understand that the sampling is done at 44.1 kilohertz means every second we are taking 44.1 into 10 to the power 3, 44.1 thousand, so 44,100. Every second we are taking 44,100 samples out of the signal, and each of those sample has 16 bits in it. So you have a total duration of the song. So first convert the whole duration into seconds, then calculate how many samples were made, and then multiply that sample number with 16 to get the total number of bits produced of this file. Go. Try, give the answer in the chat menu. That's a lot. Yeah, 2.4 into 10 to the power 8. That sounds like a correct number, or it could be 2.40, but 2 is also good because we're gonna get 0 anyway. Yeah, I got the same number as Abiya's. I want other people to try and get a number and share with us in the chat menu. Armine, are you here? I think I saw Armine doing that class. He left, I think, or is he still here? Where is Armine? Nope. He started, but I think then he left for some reason. Whatever. Okay, so that's the answer. You got the idea how to do this thing. We'll move on, and then we have this thing. Okay. Yeah, this is a very nice question. This is a very nice question. Let's have a look at this question. I'm skipping these two questions. We talked about the cross-linking and the coaxial cable benefits in the earlier class. So you should be able to do this. If you haven't do the last class, do the last classes from the YouTube lectures and read through the document. If you still can answer it, you can ask me in the next class. No big deal. I'll help you. I'm going for the 8B. A wire pair has a length of 1.4 kilometer and it is connected to a receiver as illustrated in figure 12.1. The constant noise power in the wire pair is 3.8 into 10 to the minus 8 watt. For an input signal to the wire pair of 3.0 into 10 to the power minus 3 watt, the signal to noise ratio at the receiver is 25 decibel. Calculate the attenuation per unit length of the wire pair. Okay. This question is actually not so difficult. You can find out the total attenuation value pretty easily. 10 log P okay, no, there is a certain thing. Attenuation per unit length. আমি ভুলে গেছি এই ম্যাথটা কেমনে করতে হয় দাঁড়া এই ম্যাথটাতে একটা গন্ডগোল আছে এই যে এখানে you can see there is this because this is a wire pair there are two wires over here so there is a thing about making this thing 1.4 kilometer into 2.8 kilometer but there is a certain location where you have to do this. I'm trying to remember this thing. I mean either we have to make this thing double or we have to make this thing double. Which one I forgot. The constant noise power, let me read it. The constant noise power in the wire pair is for input signal to the wire pair. For input signal to the wire pair, that signal to noise receiver is 25 decibel. Why is this difficult? We have a signal to noise ratio given. We have a noise given, so we can find out the output from the first part, and then we can find out the attenuation. Okay, let me try to solve this. I'll try to solve this. Other than looking at the mark scheme, I'm going to try to solve this. Okay. So, first thing first. No. Yes. So, signal to noise ratio is 25 decibel. So 25 equals to 10 log P out by P noise, which gives us 10 to the power 2 to the power 5 equals to into P noise equals to P out, which means P out equals to কত হয় এটা দেখা দাও একটু I'm getting 1.20 17 10 to the power minus 5, and then attenuation equals to 10 log P in by P out decibel. This should be equals to 10 log 3.0 into 10 to the power minus 3 divided by 1.2017 10 to the power minus 5. I'm taking so many decimal places over here because this is an intermediate number. I don't want to get caught up in the rounding of error. That's why I'm taking so many decimal places. You can take less, but I prefer a bit longer for intermediate numbers. It gives me peace of mind. So hold up. Oh, okay, so 3.0 10 to the power minus 3 divided by answer log of answer into 10. 23. I'm getting 23.97, 24.0 decibel, and that is gonna happen over a duration of 2.8 kilometer because we have two pairs over here. So oh no, sorry, I don't have to do this double because the question is asked for the per unit length of the wire pair, not for a single wire pair. I don't have to do that. Sorry, my bad. I misled you. So 24.0 divided by 1.4. 70.1. Am I correct? Yay! Worked. So I was a bit misled because I considered I have to double it. But I think there is a question where we have to double it. There is a certain question where the length had to be doubled. Anyway, this is done for. One working টা কি বুঝছো সবাই এখানে কি হইছে? Sorry. এতগুলো এখানে কেন? এই ওয়ার্কিংটা কি বুঝছো সবাই? দেখো, we are provided with the signal to noise ratio equation. So first, using the signal to noise ratio, we calculate out the output power, which is the intermediate value that is available on both the equation. Then using the output power and input power was already given in the question. Using these two ratios, we calculate the attenuation. And then once we get the attenuation, finding out the attenuation per unit length means total attenuation divided by the total length of the wire. That gives you the attenuation per unit length, that much decibel per kilometer. That basically works. Any questions about the working? Anyone?
No, sir, it's pretty clear.
Sir, why did they mention?
What?
Yeah, sir, why did they mention constant noise power? Like noise power, it being constant.
Noise power in constant means that from the starting of the communication channel all the way through the communication channel, the total noise, persistent noise to the wire pair is this much. This happens because of the intrinsic property of the channel. This is a wire pair, so it is highly affected by the electromagnetic fields around it. So that's the noise value that we have to deal with, which we cannot come across. That is a property of the whole communication channel, entire of it.
Okay, sir.
Then we have these stuffs, and then statistics rather than direct transmission have radio frequencies. Microwave of such application in one case for transmission using a wire pair, coaxial cable, microwave link. Such applications are in each case for the transmission of signals using a wire pair, coaxial cable, microwave link. A wire pair can be used for short distance communication, like an intercom within a building. That's the most common example that I can think of. A coaxial cable can be used for cable TV, most common use. And a microwave link can be used for telecommunication or cellular communication or long distance talking, if that's a word. Number 10A, linking a land telephone to the local exchange. Okay, connecting an aerial to a television. Yes, definitely. Linking a ground station to a satellite. Linking a ground station to a satellite. Okay, these are all examples. So let's have a look at the mark scheme. For out of characters, essentially, can is adequate to describe their searched application. Example, for example, when one application is to link an aerial to a television, it is not sufficient to simply state television as the answer. Okay, you have to elaborate your answer. So mentioning television is not good enough. Television তো অনেক কিছু থাকে, পাওয়ার কেবল থাকে, ক্যাথোড অসিলোস্কোপ থাকে, অথবা এলসিডি প্যানেল থাকে, এলইডি প্যানেল থাকে, op-amps থাকে, বহুত কিছু থাকে. So should mentioning the television is not good enough. So which part of the television has to be connected is very important. Yeah, makes sense. Makes sense.
Sir, aerial মানে তো antenna, right?
Yep, yep. These are synonymous words. We did this problem. Did we do this problem? No, we didn't do this problem. I'll do this problem. Get selected. Come on. Okay. Let's have a look at this one. Oops. Okay, let's use a different space. Let's get rid of this one. Put it right here. Okay. So look, the question says that a cable used for the transmission of a signal. এখন পাবে খোলা, hold on just a second. তোমার ম্যাডামের কিছু লাগবে ইংরেজি করে যাও আর খাতায় লেখো. All right. So let's have a look. A cable is used for transmission of a signal of a signal has an attenuation per unit length of 2.1 decibel per kilometer. There are no amplifiers along the cable. The input power of the signal is 450 milliwatt. Calculate the output power of the signal of the cable for a length of 40 kilometers. This is pretty simple. So input power দেওয়া আছে, আমাদেরকে output বের করতে বলছে. So all that we need is the attenuation value, which you can find out is in the distance and the attenuation per unit length. So in this case, the total attenuation would be attenuation equals to হবে হচ্ছে 2.1 into 40. That gives you কত? 84 decibel. And then you can just go ahead doing this. 84 equals to 10 log P in by P out. তো এখানে তোমার P in দেওয়া আছে, এটা হচ্ছে তোমার ফর্মুলা, এখান থেকে হিসাব করে তুমি আউটপুট পাওয়ার বের করবা. I don't want to do the calculation. এখানে আউটপুট পাওয়ার কত আসে আমি এখান থেকে দেখে ভরা দিচ্ছি. কত নম্বর এটা? কোশ্চেন নাম্বার 10B. Output power আসে হচ্ছে 1.8 into 10 to the power minus 99 watt.
Yes, right.
1.8 minus 9 watt. Okay. And then it says the minimum acceptable signal power in the cable is this much. Minimum acceptable signal power. এই পার্টটা ইম্পর্টেন্ট, যে এই কোশ্চেনটা ইম্পর্টেন্ট, এই কোশ্চেনটা বুঝা জিনিস আছে, খেয়াল করো সবাই. The minimum acceptable signal power in the cable is 7.2 into 10 to the minus 11 watt, which means your signal output power cannot get lower than this. Calculate the maximum uninterrupted length of the cable. Maximum uninterrupted length of the cable means basically this is another wording for calculate the minimum distance after maximum distance after which a repeater station is required. So signal strength as so the as you send in from the input location, the signal strength is going to decrease. Then whenever it will decrease to this value, that is the point where you must place an amplifier station. You can choose to place it earlier than that, which is good, but you cannot place it lower than that because this is not recommended. So we're trying to find out the maximum uninterrupted length. So what we're going to find out is whenever we have this much output power, if this is the output power, how much attenuation are we going to have? So first we calculate that value. So এখানে attenuation হবে হচ্ছে 10 log P in by P out, which is a bit smaller thickness. That gives us 10 log এখানে P in কত ছিল 450 মিলি আর P out হচ্ছে 7.2 10 to the minus 11. 7.2 10 to the power minus 11. দেখো তো এটা কত আসে? Ten into log bracket 450 50 10 to the minus 3 bag 7.2 10 to the minus 11. I'm getting at
95.
98.0. 98.0. So thank you. This is the amount of attenuation that we're going to have over here if the signal gets dropped down to this much power. And then the question says that we have 2.1 decibel per kilometer of attenuation. So each kilometer they reduce this much. So we just have to find out how many kilometers are required to make this much attenuation. So that's basically very simple. 9.8.0 divided by 2.1. So this is basically decibel. This is decibel per kilometer. So whenever it gets reverted, you get kilometer. By 2.1.
46.7 kilometers.
46 point. I'm going for 46.6 because I used the answer value. I didn't use 90.0 exactly. 46.6 kilometers or 47.0 kilometers. You can write 47.0 kilometers. So this question is to calculate the maximum uninterrupted length. I think that's the correct answer. I'll have a look at the mark scheme. What it says 47 kilometers. Okay, this is the 2SF value. So yeah, 47 kilometers. Works. They have stick with for 2SF value throughout the working. I mean, you can choose to go for 2SF. Works for me. I prefer 3SF values. Candidates has mixed up success with this part of question. The most frequent error was to use an incorrect value of the input power in their calculation. Yeah. Okay, once again, we have input signal. We have to find out the individual bit values for different position time frames. You have to place this. Extend whether the sampling frequency is adequate to enable the output to be produced. This is actually an interesting question. Have a look. In this question, the sampling frequency was done the sampling was done for every 0.25 milliseconds. So these 10 divisions are our sampling instances. So we're gonna have 6 going up, and then 10 going horizontal, and then 14 going horizontal, and then 15 going horizontal, and then 10 going horizontal, and then 9 going horizontal. That's the value that we're gonna have. So I'm going to try to draw this graph onto this one to give you a bit of an idea, because I want to really elaborate this question number C. I want to have an elaborate discussion for this one. So let's try to fill up this graph with straight lines. Hey. So let's choose this one, maybe red, thickness, this one. So we're going to have this. Then we're going to have this. Then we're gonna have this. Then we're gonna have this. All these red dots that you can see, you don't need those. I'm just have to click my mouse pointer at a certain point to so that I do not move this thing, other than if I don't do that, I'm gonna start moving this one. So I just have to give a dot somewhere else to deregister that input. That's the way I'm doing this. And then this one. Comes down to this. Although this graph does not necessarily shows beyond this point, but I know because it is 0.25 millisecond for every register. So this will go on like that. You don't ever have to do this graph for your actual question. The question doesn't require that. I'm showing this to you to give an idea that if we do a sampling of this frequency, have a look, we are practically missing out a lot of detail of this original analog form. We are missing out this whole increment. We are missing out this lowest point. We are getting almost the increment of this part because maximum was registered maximum. But then again, we're missing out this entire plateau over here. So we are missing out this whole information. This is showing that this was horizontally fixed over here and then just got reduced. So we are not capturing enough detail of this original analog signal with this sampling frequency. So that's what I want you to appreciate, that this sampling frequency is not good enough. Not high enough, actually. Good enough is a pretty big word. It's not high enough to capture all the individual variations for this detailed analog signal or this varied analog signal. So that's the information. So, but how do you put it into words to score marks out of it? So question number C, 11C. Let's have a look at the mark scheme. This is a 2-mark question. Have a look. On option C, what we have is 11C, yes. Significant changes in detail of V between samplings. Significant changes in detail of V between samplings, so frequency too low. Let's read the question one more time. Explain whether the sampling frequency is adequate to enable detail of the output V to be reproduced. So the question is asking us that explain whether the sampling frequency that we have is adequate to enable detail of the output V to be produced. So what I showed you in this figure is that what the output is going to look like for this graph, for this sampling frequency. Does this output capture enough detail of the original input signal? The answer is no, because there are significant variation of the original signal in between the sampling values. So here we have one sampling, here we have another sampling, but between these two sampling, we had a significant change of the original signal, and over here as well. So this sampling frequency is not adequate, or it's not high enough. That's the mark scheme wording. Significant changes in detail of V between samplings. So frequency too low. Examiners report देखो. Many answers consisted a statement with frequency either too high or too low without justification. Others quoted Nyquist, but again, any conclusion was not sustained. This has nothing to do with Nyquist. Nyquist has nothing to do with these graphs. Comparatively few made the reference to detail of change in V between the times at which the samples took place. So this was mostly a wrongly answered question. Many of the students did not even understand how to approach this question in the first place. But you should not be, because you should understand why this is happening, because we're missing out a lot of detail in the sampling process that is getting cut off in the sampling process, which would not be reproduced in the recovered DAC, digital to analog conversion. So that's something that we want to avoid.
Sir?
Yes.
Is sampling rate the difference between high quality and low quality microphones?
Both of these factors play a large role. Sampling frequency plays a huge role, and also the bit number also plays a high role. If you want a good quality sound, you need high sampling frequency along with high bit number. Both of these factors would increase your file size. So whenever you have to compare between file size and quality, there is a halfway point that we usually come by. So you have to, you can have very high quality files which are very large, so they can take a lot of storage and very slow to transfer over slow connection of internet. That's one choice you can do. Or you can have low quality files which can be transferred pretty well. So, or you can choose a halfway point. So it depends upon what application are you going to do. If you're going to play your song, let's say on a waiting tone of a intercom service, a very low quality file is good, because no one is basically calling an intercom service to listen to the music that they play. But if you are planning to listen to a music for your own entertainment value, then that can differ from people to people. Does it make sense?
Yes, sir.
Beautiful. I'll pick up more questions from this worksheet next class. Hopefully, it's 9:33. I feel burned out, so I'd like to come to today's class.
স্যার
Yes.
স্যার আমাদের বুকলেট 3 পর কি আর কোনো বুকলেট আছে মানে
No. For paper 4, you have
আচ্ছা,
altogether
এটাই?
3 booklets. Yes, that covers the entire syllabus, and you have the paper 5. So
জি স্যার
for your A2 course, you have altogether received from me 5 pieces of binded booklets.
স্যার ওই চার্জ পার্টিকেল একটা টপিক ছিল না বুকলেট 2 তে
Yes.
এখানে স্যার ওটার কি কোনো নোট আছে মানে
Nah, charge particles
Acha.
notes because the chapter charge particles. I mean, to be honest, I'm charge particles worksheet তোমাদেরকে করাইও নাই. I leave it in
হ্যাঁ
your
স্যার
hands. You try. I want you to try this, and if you get stuck, I'll definitely help you with the stuck problems. But here's the deal: the charge particle chapter basically handles a combination of electric field and magnetic field individually
ইলেকট্রোম্যাগনেটিক ইন্ডাকশন
or simultaneously. So how they would bend, whether they're going to go in straight line, how they're going to, so how, what's going to be the shape of their curvature, all of these things mixed together. So this did not actually require to be an individual worksheet, but someone made it into different worksheets. So that's it doesn't have any individual theoretical notes. That's why we didn't ever discuss this problem.
স্যার
So after finishing the worksheets, can we just have a solve class for them later?
Yeah, definitely. I mean, we're gonna start our chapter-wise top test from there on January, and then we're gonna have full syllabus marks on February, March, and April. So these remaining days that we have for the month of December, and we can also schedule extra classes if you kids want. But these remaining classes are basically aimed to solve all the sorted out problems in your worksheets. So if we have worked attempted some worksheets, and then you would like to have some discussion about some of the problems, then we're all for it. For next class, I would like to continue this worksheet for a couple of questions, and then if you feel like, you can bring up questions from other worksheets as well. Yeah, that makes sense, everyone?
Okay, sir.
স্যার
Thank you very much, guys. Good night.